Hello viewers, I am Savitha Mary, Assistant Professor of Mathematics working in St. Joseph College of Arts and Science, Kadalur. In this video, we are going to discuss about the topic countability. For this topic, we need to review some definitions like one-to-one, on-to, one-to-one correspondence and equivalence. These are the definitions we are going to review for this concept. See the first definition, one-to-one function. So one-to-one function is nothing but every element of the set A is mapped by the function f into the different element. So consider the function f is from A into B. From that function, every element of A is mapped to the different elements of B is called one-to-one function. See the example, f of x equal to x squared with the region 0 less than or equal to x less than infinity, which is the positive region. Inside the positive region there is a mapping 0 less than x less than infinity to 0 less than or equal to x less than infinity. The function is f of x equal to x squared is one-to-one function. So then second example is g of x equal to x squared with the region minus infinity less than x less than infinity is not one-to-one function because there is no mapping by different element. See the image in the next slide. See the first image, f of x equal to x squared. There is a mapping from 1 tends to 1. That is x equal to 1, x square is also 1. Next x equal to 2, we will get the image 4. So 2 mapping to 4 and 3 mapping to 9. So there is an 1-to-1 mapping. See the next image, minus 1 mapped to 1 and 1 mapped to the same element 1. And also minus 2 mapped to 4 and 2 is also mapped to the element 4. So there is two elements mapping to the one image, one element in the set B. There is no different mapping, so that it is not one-to-one function. Next definition is one-to-one correspondence. One-to-one correspondence is the function satisfying the two conditions one-to-one on-to. The function satisfying the both mapping one-to-one onto is called one-to-one correspondence. Next definition is equivalent. When we said the sets are equivalents, if the mapping satisfies the condition one-to-one correspondence between the set A and B, means A and B are called equivalent sets. Now we see the main definition, countable. A set is countable means it should have a finite size, or there is a one-to-one correspondence with a natural number or a positive number I. A positive number is represented by I. That is, we have to show the element of the set can be put in order so that no element will even be repeated. That is, no element will ever be repeated and no element will ever be missed out. So every element should be counted and every element should not be missed out. That is called countable set. If the set is not countable, then it is called uncountable set. The set of integers are countable set. This is the example. And see the image. We can count the integers like the way by using the natural number. This is nothing but you can use a positive integer or natural number. And see, the first value 0 is mapped to the number 1, and 1 is mapped to the number 2, and minus 1 is mapped to 3. So like this way we can count in an arranged order, and no number is missed out in this order. So every positive and negative values will be arranged like this, and we can count the positive and the integers like this way. So the integers is countable set. See the next example. The set of all rational numbers is countable, and the rational number is nothing but p divided by q, and p and q are positive integers or negative integers. So and then see the image. This is also counting order by the natural number, and 0, 1 by 1, minus 1 by 1, 2 by 1, 1 by 2, minus 1 by 2. Like this way we can count each and every element of the rational numbers, and we can follow another method also. I will include the slide. See the image. By the arrow you can count the rational numbers, and the first number is 1 divided by 1. Adding the numerator and denominator, you will have the number 2. Next number is 1 by 2 and 2 by 1. So adding the numerator and denominators, you will have number 3. The next numbers are 3 by 1, 2 by 2, 1 by 3. So adding the numbers, you will have the number 4. So likewise you can mention the arrow, and then you can count every number of the rational in this order. I have mentioned only the positive numbers. Like this way you can count the negative numbers also. So this is the procedure to counting on rational numbers. So we conclude the rational numbers also countable. It's over. So we will see some theorems in the next video. Thank you.